Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
So, concerning quantum physics, energy, as we know it, exists in discrete packages called photons. So when you have a particular amount of energy, it's actually a number of photons that are flowing, So it's not a continuous thing. It's in discrete, just like drops of water that make up maybe a quantity of water in a pocket or in a container. So when energy is transferred, this also happens in these discrete packages, are multiples of the unit quantity, which is the photon at the time. And of course, the energy of one unit package of photon can be found using equal to HF, right? Where H stands for what? Planck constant. And F is frequency. That already tells us that the frequency affects the amount of energy a photon has. So a photon of a red light we have a different amount of energy than a photon of blue light because they have different frequencies. The higher the frequency, the higher the energy, Though they are photons, that's same unit, like same volume of energy, so to speak, but different amounts, All right. And of course, we explain how you got H equal to hc over lambda, because c is the speed of light and lambda is the wavelength, because f is speed over wavelength. So it's the same thing as hc over lambda. All right. Let's move on to the next page. Momentum of a photon. I'm on the next page.
Yes, photons have momentum even if you don't have any mass.
Because photons have momentum, because energy exists in particulate nature. In other words, energy itself is a particle. An energy is actually a dissipated particle. Just like a particle is like a concentration of energy. So you can transform a particle to an energy. You can transform energy to a particle. These are some of the newest discoveries in science, that when you have like light is not just a wave, it is also a matter. We call it dual nature of wave. A wave exhibits a property of a wave. Some of the properties of a wave are reflection, interference, and all that. It also exhibits properties of a matter. We talk about that later. Diffraction is also one of the properties of a wave. Okay, photons have momentum even though they do not have mass. The momentum of a photon is inversely proportional to its wavelength. Okay, I will explain to you how we came about that. There's a way you can show this. The momentum a photon of energy has is inversely proportional to its wavelength. That already means that it is proportional to its frequency, isn't it? Okay. If it is inversely proportional to its wavelength, then it means it is proportional to its frequency, isn't it?
Yes.
Okay. So you can think of it like that the momentum is proportional to the frequency of the wave. Just like the energy is proportional to frequency. The momentum is proportional to frequency and inversely proportional to wavelength. All right. So the constant of proportionality is also the Planck constant, right?
That's H lambda.
No, the constant of proportionality is the Planck constant and h.
H over lambda.
The real equation is this. See, can you see what I'm circling? As it's shown at your end,
Yes, that's momentum
is inversely proportional to
wavelength.
wavelength, or momentum is proportional to frequency. The constant of proportionality is
Planck constant.
Planck constant. Okay. All right. So you can also think of it like this: momentum is proportional to frequency, if you like. All right. If we replace the wavelength with C over F, you know how we came about C over F?
Yes.
So we'll come up with this formula. P equal to momentum is equal to HF over C, isn't it?
Yes, if you flip.
All right. And you know what HF is?
Yes. Energy.
Energy. Isn't it?
Yes.
So that means momentum is equal to energy over C. Make energy the separate formula.
That's CP.
PC.
Oh, yeah, PC over C.
Pardon?
That's PC over C.
Or that's rho C. Is that what you are trying to say? So energy is equal to rho C. And that's what the scheme was trying to show us. Can you go back to that scheme? The last objective.
Understand that photon has momentum and that the momentum is given by E over C.
E over C. Because if you make E the solid formula, you have what?
If you make that rho C.
E is equal to rho C. Right? All right. We can take this further. What is rho?
Momentum.
And what's momentum?
Mass and velocity.
Mass and velocity. Okay. And speed, C is what?
Speed of an electromagnetic wave vacuum.
Okay. All right. I want us to move it further. You will see how we come up with how Einstein came up with the famous equation.
Sorry, MC squared.
Yeah. So let's see. You see how all of this come into play. So we know that P is equal to E over C. Okay. I want to show you something. Look at this place. E is equal to HF, which is HC over lambda, which is PC. We know that E is equal to PC, right? And you know momentum is MC, isn't it?
Yes.
And so MC times C will give us
MC times C, that's MC squared.
MC squared. So E is equal to,
MC squared.
that's the Einstein's equation. You are familiar with it?
Yes, it's everywhere.
It's everywhere, really. All right, so E is equal to MC squared. Okay. Let's look at some of these questions. Look at this first one.
What page are you on?
The last page, page 20.
Okay. A low frequency radio wave has a frequency of 200
Kilohertz.
What is the momentum of a radio wave photon with this frequency? Give your answer in scientific notation. Okay, so what do you do? What is the momentum? Okay, so use PC equals to HF.
Because E is equal to PC.
Yes.
So you can remember that E is equal to PC or rho C. Let's use the right word, rho,
Yes.
which is equal to HF,
Yeah.
right?
Yes. So what you do is to make P subject to the formula.
That's all.
Yes. And that's all the question.
So P rho is simply equal to HF
over C.
HF over C. All right. That's what was done. Okay. You express to the unit of momentum, which is kilogram meter per second.
Yes.
Look at this second one
On Newton.
on Newton's seconds. Impulse. It's better to express it in kilogram meter per second because it's about momentum. All right. This second one says a laser produces 4.0 times 10 raised by 27 photons, each with a frequency of 4.25 times 10 raised by 14 hertz. What magnitude of momentum does producing this photon impart on the laser?
What's magnitude? Which is the frequency? Okay. So first, I think we calculate the individual momentum of each photon, and to do that, yeah, the magnitude, okay, momentum, okay. So yes, we calculate the individual momentum of each one. So again, using the equation PC equals to HF.
Okay. Or P is equal to HF over C.
Yes. Then when you now need the momentum also to the formula, multiply the individual momentum by the number of
Photons, which is N.
Yes.
The momentum of one photon is HF over C from equation H over lambda. All right. Okay.
Now
Multiply to get the total momentum, isn't it? All right. Okay. Good. You know, we've already shown that the momentum of a wave is inversely proportional to
wavelength.
the wavelength. That means it's directly proportional to its frequency. So the momentum is inversely proportional to the wavelength, which means it's directly proportional to the frequency. The constant of proportionality is the Planck constant. Okay. All right. That noted. Photoelectric effect is one of the phenomenon to prove that energy is transferred in discrete quantities called photons. Now, photoelectric effect is what happens when electromagnetic waves incident on a particular kind of metal liberates electrons from the metal. You know, it's just like beaming an electromagnetic wave. Give me an example of an electromagnetic wave. Radio wave or light. Let's use light for instance. It can happen with any electromagnetic wave.
Light photons heat.
Yes, once electromagnetic waves hit a metal, they liberate electrons from the metal. You know, when we get to X-ray, production of X-rays, we discover that it is the reverse. In X-rays, we accelerate electrons. We accelerate electrons, and when those electrons accelerated, it suddenly stopped. They hit an obstacle, a target. X-rays are emitted. I don't know if you can get the difference. The reverse.
I know it's the reverse.
It's the reverse.
Yes.
Because here,
Light liberates electrons.
Electrons, but in the production of X-ray, electrons causes electromagnetic wave to be emitted instead. So photoelectric effect is the reverse process of generation of production of X-rays and a number of other electromagnetic waves like that. Okay, so that's the diagram. Electromagnetic waves incident on a metal liberate electrons. Now why does that happen?
The electrons absorb energy to escape.
Excellent. In fact, that's beautiful. The electrons absorb energy to escape. In fact, one electron absorbs a photon of energy. and escape. That is, like I told you, that's one of the proofs of quantization of energy.
Yes. In fact,
So-
that one is one to one.
1 to 1. So 1 photon for 1 electron. 1 photon for 1 electron. So what it means is, when we increase, think about it now. You are coming to, all of these things are coming to a focus. It means that when we increase the number, remember the word is the number of photons that are coming in. That means there will be more electrons that can be emitted, because you have more electrons that can catch each photon and be emitted.
Yes.
So more photons will liberate more
Electrons.
electrons,
Number of electrons.
more number of electrons. Remember, more photons does not necessarily mean a higher energy.
Yes. It just means
It doesn't really mean a higher energy. It could be the same red light or the same blue light. Anyways, I don't want to jump the gun. Let's move forward. So look at this. Are you here?
Yes, I'm.
Now, there's something that is usually a recurring question, a recurring issue in photoelectric effect.
Yeah.
Like when you are asked to explain why the maximum kinetic energy of photoelectrons is not dependent on intensity, whereas the photoelectric current is proportional to intensity, or depends on intensity.
Yeah.
Do you have an idea why the maximum kinetic energy of the photoelectrons, that's the electrons that are emitted, does not depend on intensity?
Was
However, excuse me, the current depends on intensity. The question is, why does that kinetic energy, that maximum kinetic energy, why does it not depend on intensity?
because
Whereas current depends on intensity.
I don't know. Because of the work function, like the intensity, I don't know how to. It doesn't matter.
Okay, you see this. See this as imagine, like the illustration I gave you earlier. Are you still here?
Yes, I am.
Look at imagine a given metal of work function 22 joules
Yeah.
for same intensity of different light. Intensity, intensity is not about the photon energy. What determines the photon energy is the frequency. Energy of a photon is equal to hf, is it not?
Yeah.
The energy is hf, Planck constant times frequency. So that's what determines the energy. That's what determines energy. It is not intensity that determines energy. Okay.
So what?
We said that the incident electromagnetic wave having a particular, maybe a number of photons, will interact with the individual electrons. One electron will absorb one photon and be emitted. Another electron will absorb another photon and be emitted, and so on. Okay. So if we increase this is how I will explain it. I want to use this to explain this. Let me see. I have an explanation somewhere. Go to page 6 of 20. Oh, no. Before we talk about this, we need to look at work function. Let's talk about work function. I'll get into that. Are you ready?
Yes.
Now, the work function is the minimum energy that the incident light or electromagnetic wave must have before it can liberate an electron.
That's work function.
The work function. Yes. What it means is electrons that can be emitted by a red light or by a blue light, because a blue light has a higher energy, may not be emitted by a red light, which has a smaller energy.
Oh, I guess.
Because
They don't have the minimum amount.
Red light does not have the minimum amount of energy needed to liberate the electrons. So the minimum amount of energy that the incident photon must have is the work function. Anything extra will now give the emitted electron kinetic energy. You know, first of all, the work function is just enough to cause it to come out.
But
anything extra will now give it the kinetic energy with which it needs to move. So how do we make it higher? How do we make the photon to have a higher energy?
Increase the frequency.
Increase the frequency. So if a red light is sufficient enough to produce the work function for a particular photon used, if you now use a blue light that has a higher frequency, which means higher energy, it will have more kinetic energy to move.
Yes.
That's the implication. It will have what? More kinetic energy. It doesn't mean more electrons, so it's just more kinetic energy. And I will explain. You will see how all of these things add up. Okay, so the work function is the minimum energy that the incident light or electromagnetic wave must have before electrons are emitted. You know. Now, when a wave with photons of greater energy than the work function strikes on a metal, the extra energy provides kinetic energy for the emitted electrons. You know, you need to also know that the kinetic energy of the emitted electrons will not be the same, because some might be coming from the middle of the metal, some from the surface. The ones from the surface wouldn't need to overcome the obstacle of intermediary atoms inside the metal. You know, the ones liberated from the surface will probably move faster than the ones, or move at a greater kinetic energy than the ones from the interior of the metal. Because the ones from the interior of the metal will still waste energy. You just imagine, let me give you an answer. Yeah, they waste energy for coming. Assuming the work function is 40 joules. It's what?
40 joules.
And then we have a photon of light that can produce 41 joule, or let's even say 42 joules. 42 joules. You know, the extra 2 joules will give the emitted electrons kinetic energy, isn't it? But you know that the electron that is in the interior of the metal may waste the 2 joules to be able to come to the surface. So that's why the ones at the surface will have a higher kinetic energy than the ones from the middle or from the base of the metal. So the kinetic energy of the emitted electrons is not the same, because they are coming from different regions in the metal. Alright, so you can see that the energy of the photon is equal to the work function plus the kinetic energy, that's the extra energy. Did you get that?
Repeat.
Just like the example I gave you, 42 joules. If the work function is 40 joules, if the work function is what?
40 joules.
And the photon has 42 joules. So the extra 2
Would be used
for kinetic is, I'm just talking about, assuming it has already overcome all the obstacles.
to provide extra
Kinetic. So the energy of the photon incident is equal to work function minimum plus extra kinetic energy. So that's the formula you find in the next page. Go to the next page. Energy of a photon is equal to the work function plus that extra kinetic energy. Now, the frequency for that work function is what we call threshold frequency. So the threshold frequency is the minimum frequency of incident light for electrons to be emitted. You know that? Because, of course, if the energy is going to be higher, it means higher frequency. So that smallest energy needed, we also have the minimum frequency. Any frequency higher than that means higher energy. So the extra will provide kinetic energy. So if you now...
frequency related to work function.
Yeah, pardon?
Threshold frequency
is related to work function. Threshold frequency is the frequency for the work function. Threshold frequency is the frequency for the work function.
Threshold frequency.
Pardon?
H times threshold frequency.
H times threshold frequency is the work function. It's just like like I said, if we have 50 joules and then 50 joules coming in and the work function is 40, obviously we're going to have 10 extra for kinetic energy. Okay, now let's look at, I gave examples. If you have a red light having 18 joules, a blue light having 32 joules, these are just for the sake of explanation. It's not necessarily what will happen. A violet having 40 joules. Now for a metal with a work function of 22 joules, which photon will be able to emit electrons?
For a metal with a work function
Of 22 joules. You know, red light has an energy of 18 joules. A photon of red light has an energy of 18 joules. A photon of blue light, 32 joules. A photon of violet, 40 joules. But the work function for that particular metal is 22 joules. So will red light be able to emit electrons? Because it is below the minimum energy required to emit electrons. So only blue light and violet. Which one will emit electrons at higher kinetic energy? Obviously violet, because it will have extra energy. Okay. Of course, if the energy is given, and if that energy is the work function, we can calculate the frequency, the threshold frequency, because E is equal to Hf naught. So we can see that the number of electrons emitted, which of course is the current, depends on the intensity of the light, because more photons of light that falls on the metal means there will be more electrons that can absorb each photon and be emitted. For instance, in this diagram we have three, assuming just for illustration, we have 3 photons of light and 3 electrons interacted with the 3 photons and were emitted. So if we had more photons of light, there will be more electrons that can interact with it and be emitted, or with them and be emitted. So more photons means higher intensity. In other words, higher intensity means more photons. That means the intensity of light affects the number of electrons that are emitted, which of course is current. More electrons means more current. So to increase the photoelectric current, that's the current, you have to increase the intensity of the light. I have said that higher intensity means more photons, and that means more electrons can interact with each of those photons and be liberated or emitted. So intensity affects current. In other words, current depends on intensity of light. The photoelectric current depends on the intensity of light. But the intensity of light does not affect the speed of the emitted electrons. We have said that already. The intensity of light does not affect the speed of the emitted electrons. The speed of the emitted electrons, which is the extra kinetic energy that the electrons have when they are emitted, depends on, that kinetic energy depends on the kind of photon the frequency of that light, because the energy of the photon depends on the frequency of the light. You know, energy is HF. Energy is HF. So a light with a higher frequency, as we've said earlier, has a higher energy. And a higher energy means there will be an extra or a bigger extra energy to give the emitted electrons kinetic energy after the work function has been met. Higher energy of photon because of a higher frequency. Higher energy of photon means there's a higher kinetic energy, extra kinetic energy for the emitted electrons to move after being liberated. In summary, to increase the kinetic energy of emitted electrons, use light of a higher energy, which means use light of a higher frequency. So, kinetic energy of emitted electrons depends on the frequency of the incident photon. It depends on the frequency of the incident photon. The maximum kinetic energy of the emitted electrons depends on the frequency of the incident photon. Depends on the frequency that these light photons are carrying. The maximum kinetic energy, I said that again, depends on the energy of the incident photon. The maximum kinetic energy does not depend on the intensity. The intensity simply means more photons, more number of photons, and more number of photons will produce more number of electrons emitted. More number of electrons emitted means higher current. Alright, so that's understood based on the question I asked earlier, that the photoelectric current depends on intensity. But the photoelectric current does not depend on the frequency of the incident photon. What depends on the frequency of incident photon is the maximum kinetic energy of the emitted electrons. So maximum kinetic energy of the emitted electrons depends on the frequency of the incident photon, which of course the frequency determines the energy. So maximum kinetic energy does not depend on intensity. What depends on intensity is the photoelectric current. Okay. Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.